I got interested in simulated annealing optimization hello? Oh, that's more like it. Now we're talking. So I got interested in simulated annealing, and one of the things we like to have when we do simulated annealing is normally distributed random numbers. So let's see here. There it is. Almost all computing systems, from the lowest TI calculator, Hewlett-Packard calculators, MathCAD, MATLAB, even Microsoft Excel, all have random number generators in there, but they're uniform only. They don't have normally distributed random numbers. So,
what's the advantage of I mean, just why don't you take normal uniform and just have a wide range?
Because when you do a simulated annealing, you're trying to do two things at once. You're trying to jump out into remote regions to try to find a minimum that might be better, a lower minimum than your local minimum, but at the same time you want to do the best you can locally.
Okay.
So generally the way simulated annealing works is you start with random numbers normally distributed at a very large variance, and you jump all over the place looking for the best solution, and if you find a solution that's better than the previous one, you adopt that as your current solution, then you perturb that further with the random numbers, and as you're doing this, you gradually cool down the system. That means you shrink the variance of the random numbers, so you're searching more and more locally. So we like to have random numbers, and the paper I put in the proceedings talks about different methods for generating the random numbers, and let's have a look at it. Personally, I think that normal deviate should be something that's actually built into the calculator. Some calculators, some of the better ones, do have the normal distribution function built into them. But of course, that's not what we need. What we need is the inverse of the normal distribution to turn the uniform random numbers into normal deviates. So let's see what we have here. Okay, so what's a distribution? Well, I think most of us know that, except for one particular person that I happen to know, and she's right back there. But that's just the probability that a function is less than a certain value. So it's all related to probability theory, and so I'm working with the HP35S. If Sam were here, I'd say thank you, Sam. I don't see him today.
He's in route to Vegas, right?
But so we have on the 35S we have a uniform random number generator. It does some operations faster than others. Now, if you look in Knuth's book from the late 1960s, he has a whole section of one chapter on fast multiplication. And it seems finally to have happened, because when I clocked some of the instruction times on the 35S, it turns out multiplication, subtraction, and addition all take the same amount of time. So we're no longer restricted to try to avoid multiplication as a slow operation, as once was the case. This probably overthrows a lot of what we know about numerical methods. So let's see what we have. Okay, here you have the normal probability density function. It's an intractable integral. It's just its own function, and if you look at the shape of that curve, you basically have an S-shaped curve. Out at the left end, it goes to 0, and then it goes up through the point 0, 1/2, and then at the right end it goes up to +1. So let's see where this goes. So here's some of the ways we can try to generate normal distributions. Okay, the probability integral transform. That's sort of the standard one. It's in the Handbook of Mathematical Functions. You just apply a function to the uniform random number, and you end up with one that's normally distributed. Von Neumann acceptance rejection. Basically, what you do there is you have a function that sort of looks like the normal probability density function. But the problem here is you have to generate two uniform numbers. One to be the candidate, and another one to decide whether or not you're going to accept it. And because some of them you will reject, you end up maybe generating 3 or 4 uniforms for every normal deviant. And it turns out that on the 35S, generating a random number, the rand command is a slow one. So you want to make maximum use of your uniform random numbers. Okay, you can use several uniform deviates. You sum them. Everybody knows if you take the sum of 12, that you get something that looks like a bell curve, and it has the right. If you take the sum of 6 minus the sum of another 6, you end up with something that has a mean of 0, and the standard deviation is 1. The problem is that the fourth moment it isn't quite normal. It's a little bit weak in the tails, and it has an absolute limit, whereas the actual normal distribution has tails that go out to infinity. There's a technique using the ratio of uniform random numbers. Now, if you look at the ratio of two random numbers, it opens up a whole world of probability theory, different kinds of distributions. But if you just think for a moment about the ratio of two uniform random numbers from 0 to 1, and it turns out to be uniformly distributed if the ratio is less than 1, and then it falls off as 1 over x. It falls off as 1 over x for the ratio greater than 1, and because it falls off of 1 over x, it turns out this thing has an infinite variance. The integral for the variance doesn't converge. It's sort of like the Cauchy. Then there's a Box-Muller transform. That is pretty good, actually. You generate two random numbers. You generate two normal random numbers out of two uniform random numbers. The problem with the Box-Muller is it involves taking both the log and the square root. So, but you do end up not wasting any uniform deviates, because although you use, every time you do the algorithm, you use two uniforms. What you get out is two normals, so it's, you're averaging 1 for 1. Then there's a ziggurat. Now, a ziggurat is a stepped pyramid structure, and Marsaglia's ziggurat is a step function approximation to the normal distribution curve. And basically what they do there is generate two uniform random numbers. One is used to index into a table, and then from the table you do a linear transform. And you have an upper and lower linear transform, and as long as you're below the lower linear transform, which happens like 99.9% of the time, there's nothing more to do. But the 0.1% of the time that you're between the two limits, you have to revert back to that e to the minus x squared curve and decide whether to accept or reject the random number. And there's more, but yeah. Look at my conference papers. So This is normal distribution is used for generating other distributions. For example, the chi-squared is just the sum of squares of normal distributions. What is it? The F distribution. All the basic distributions of mathematical statistics can be built if you can easily get normal distributions. So I think this is something that should probably be built into the calculator. And if they don't build the normal deviate generator into the calculator, they should probably at least give you the inverse normal function, so you can have something that executes quickly, and you can get your own. So let's see what we have. So what do we need? It's got to be good, and as a measure of goodness, I look at the moments. It has to be fast. Well, what is fast? Well, it's like I think it was what was it, like 40 milliseconds to generate a uniform random number, and something like that. And so we'll have a table at the end of this show to see what's fast and what's not so fast. It has to be lean, okay? In the case of the 35S, your most precious resource is those directly addressable registers A through Z, and you need those for your problem. Those are the registers that are fast to access. Those are as soon as you go up into the indirectly addressed territory, you pay a nasty speed penalty. So you don't want to tie up very many of these registers, A through Z, and not too many program steps. Not because we're low on memory, but just because it's a lot of work to enter all those programs into a machine that has no permanent backup. We have no magnetic cards or disk or anything like that, so we don't want it to be too long. So let's look at the sum of 12 uniforms. Okay, you can always remember this when you're out in the field. You can use it, it'll work for you. It requires no direct address registers or pre-stored constants. It's slow, as we will see. The fourth moment is off, and the tails terminate at 6. So if your whatever model or optimization you're trying to do requires you to probe out in the far tails, you won't get them. The Box-Muller transform, once again, it's mathematically it's perfect. It doesn't waste uniform random numbers. It's easy to remember, and it does use some slow operations. Okay, Marsaglia's original algorithm used columns, and that's written up in 1968 in the standard book on computer science. It seldom wastes a uniform random number, but it does require 2 uniforms to do its thing. The bad part is it uses a very large table, dozens of columns, and each one has its own linear transformation. So to get rapid access to those, you have to put the constants of the program have to be pre-stored in registers. You can't put constants into a program on a HP 35S. Then there's a ziggurat, which I previously talked about. And now I made something just called an ad hoc ziggurat. I just wanted to use 2 rectangles in the probability distribution function, and I found it to be fast, but once again, it's a very crude approximation, less than perfect. It might work for a lot of things. Why not 3 rectangles? Well, I don't know why not 3 rectangles, but when I wrote out the polynomial equations, and then tried to optimize them under Microsoft Excel, Excel seemed to be unable to find a solution. I don't know why. It's something to look into. Now here's Leva's ratio method. It turns out, as I mentioned, the ratio of two uniform random numbers. Okay, you take one of those two uniform random numbers, call them x and y, and you transform the y. So instead of going from 0 to 1, it goes from -1 to +1, and then you take the ratio of that, and you get this crazy distribution. But if you restrict that x-y pair to a certain region of the x-y plane, and then just take the ratio of points inside that region, then you do get the normal distribution. The problem is that defining the boundaries of that region is a little bit on the complex side. It involves slow functions like log and so on. Now, what Leva did is formulate a quickly calculable polynomial approximation to that region, and that way he got speed, but he's still using two uniforms per one normal. Okay, so here we go back to ancient history, the polynomial integral transform. Okay, this goes back to a work from the early 1950s. In fact, there was a 1953 Rand Corporation report called Approximations for Digital Computers by Cecil Hastings. Now, I never knew Cecil Hastings, but I remember in the early 1980s when I went to work for Northrop Aircraft, there was an elderly woman that had an office near mine, and she mentioned to me at one time that she had formerly worked at Rand Corporation. And I said, "Oh, really?" And she said, I asked her, "Did you know Cecil Hastings?" And she said, "Oh boy, did I know him." Well, these people are all buried in the sands of time now, but here's Hastings' approximation, and I'll revert once again to the virtual laser pointer, and as you can see, how many of you can see why you might not want to use this?
Accuracy.
Vision.
Yes.
Slow.
Yeah.
Slow. That's what.
It is slow.
So that's a problem. So there's a better approximation also by Hastings, and of course suffers from the same slow problem. So let's have a look at this. You've got the slow, and then you've got all these constants that have to be pre-stored.
It's a real laser pointer.
Oh, a real laser pointer. How about that? I think the virtual laser pointer works better.
That was really virtual. It's there, but you know. Yeah.
So anyway, the other thing, if you go back to the Hastings approximation, you see it only works for one half of the inverse normal curve. For the other half, you have to use symmetry. So you have to, whatever you calculate then requires a random sign flip. So how do you do that? Do you have to like generate a second uniform random number and use that to generate a sign flip? So anyway, it turns out you don't. Now here's the actual curve. We go in with a probability, and then we come out with a normal deviate. And if you turn this picture 90 degrees counterclockwise, then what you'll see is the left half of the normal cumulative distribution function. So as you can see, this curve doesn't look so bad, except for the left end. And I thought, maybe you could maybe you could improve on old Hastings by breaking the thing into two different regions. So if you can approximate the right half by some kind of rational function or polynomial or something, that would be much faster to calculate. And if you could save the log and the square root baloney for just the left end. So I ended up with doing the log and the square root of 4% of the time, excuse me, 8% of the time, and doing just a plain polynomial for 92% of the time. So I also found that when you limit the range to just the left end, I could get an adequate approximation with just an inverse linear. And then the other thing with the inverse linear, I figured since you don't execute that very often anyway, you might as well put the numerical constants into the program code. Now, on the HP35, when you put a numerical constant into the program code, the penalty you pay seems to be related to the number of digits, the sign, and the number of digits in the exponent. So you want to round. Whenever you have an approximation like this, the numerical coefficients going into the program code, you want to minimize the number of digits. In other words, round it as much as you can without impacting the accuracy. Now, what about the random sign flip? What I do is generate a uniform number from 0 to 1, and if the number is greater than 1, I flip the sign. And I do this by storing the sign flip information implicitly in the return address stack. So here's the actual approximations that I came up with. You see, it's a linear plus an inverse linear. Now, we had the thing on continued fractions. I tried continued fractions. I tried a rational function, and you would think that if that first top approximation is so good, why couldn't you find a rational function? You know, that would be a quadratic divided by a linear that would accomplish the same thing. But I could not get the Excel solver to converge on anything, and when I tried to use simulated annealing to find a solution, that didn't want to converge either. And so, I don't know, maybe Joe could help me with that. So anyway, those are the approximations. Now you see, well, here I managed to round these off to only 2 digits. So that minimizes the time impact when you do have to revert to the log and square root. And, oh no, this is an improvement over the one in your proceedings. So, yes, the devil is in the details. Okay, here we have 2 approximations. And one of the things we would like is for the point where the 2 approximations meet, to not have a gap or an overlap. If you have a gap, there will be a little zone where it's impossible to get any random numbers. Or if there's an overlap, there will be a little gap where you have double the probability that you're supposed to. So when you optimize the approximations, you have to try to minimize the error at the endpoints. So that costs you a little bit. You might have to add some numerical constants or increase the order of the approximation. Here's what I call the final solution. After, I should say, the semi-final solution. I might want to play with this some more, but
it's okay to me.
But the way the sign flip works is that the first thing you do, you notice the recall B. Well, if you notice 0.5 goes into B, and almost almost every program I write uses the number 0.5 in it, and you want to have that pre-stored. I think that some commonly used constants, maybe they could do a survey of user code. Commonly used constants, plus or minus 1, plus or minus 0.5, plus or minus 2, 1 over the square root of 2 pi, that's a pretty common one. Those should be in the constant library, so that you can recall them quickly. If you put them into your program inline code, it's slow. So anyway, as you can see, what I do is I recall B, and then I generate my random number, and if the random number is greater than 0.5, I execute the subroutine, I turn that into a normal deviate, then I come back and flip the sign and return. But if the random number is less than 0.5, I just go to N10, which is down here, and I generate the random number and deliver it directly. So the sign flip is implicit in the return address stack. And here's a summary of different methods that I've tried. And as you can see, the sum of 12, oh, that's another thing, a slow version. The slow version of the sum of 12 is you generate a random number, then you generate a second random number and add it, and a second random number and plus, and a second random number plus. That's the slow way to do it. The fast way is you generate a first random number and store it in a register. And then you use register arithmetic, which is much faster. And the reason it's faster is because the machine doesn't have to spend its time adjusting the stack and adjusting the last X register. The machine does less work. So right there's a significant speed up just by using register arithmetic. Now the Hastings linear over quadratic approximation, look at that baby, 274 milliseconds, wow. That's slow. It's good, but it's slow. Box-Muller, which is the best I had until I started this project, that's okay too. Much better than Hastings. The sum of two rectangle distribution, it's blazing fast, but in quality it's not there. So there's the summary. And even stuff from the early 1950s can be improved upon. So here's what we have to, here's our wish list. I always like to have one of these. More directly addressed registers. How about in the next generation, maybe have a separate random number processor that always has both normal distributed, and maybe even a random flag instantly there for you to test and to store wherever and do whatever you need to do with, so that you don't have to wait for random numbers. Since when you're doing simulated annealing, you normally have a block of parameters that you're trying to perturb. It would be nice to have a block move or curtain manipulation that could run fast. And while we're at it, the reason I like the 35S is because right after we received those machines, I took the electric machines class at UCLA. It's all about transformers, generators, and motors, and lots of complex numbers. And I was the fastest kid in the class, faster than all the kids. The 2x2 and 3x3 linear equation solvers. Well, you know what? If that makes room for some of the other stuff, let them go. Now.
Whoa.
Okay, that's it.
Question answered.
Yes, question, we got time.
Yeah. Actually, this is a comment. You mentioned Excel. Excel has both the normal distribution, the density and cumulative with arbitrary, mean and variance, and also has the inverse
It has the function, but it doesn't have it doesn't have the random numbers. That in fact is what I use. That in fact is what I use in the model in the Excel spreadsheet. Let's see here. I have the Excel spreadsheet right here, and I can just show you. How do I end of slideshow? Click to exit. Okay. Now, let me get out of PowerPoint here, and let's see if I can get the Excel spread. There's an example of an Excel spreadsheet, and can you see the cursor there?
Yes.
Okay. Now this shows the left end. This is the approximation that is an inverse linear this shows the approximation and the actual inverse normal function itself. Okay, and here if you notice, you see I've actually used the Excel function there, which you see up here. There's the Excel function. There's the t. There's the minus 2 log of the square root. There's the square root of minus 2 times the log of the uniform. And then over here is the actual approximation, which is t minus this inverse linear thing. And then so here's the error, right? And then over here, by the error, I take the maximum of the absolute value of the error. That's what I use. Now, historically in curve fitting, in the past we've always used the RMS error, the root mean square. Yes, we've historically used the root mean square error, but here I wanted to minimize the maximum error, so I use the maximum of the absolute value, and then just a second here. Let me get this out of the way now. Thank you. Now this will show you some of the formula. This shows you some of the formula that I tried and what some of the results were. So there's your maximum error, and there's your numerical coefficients. But the one I adopted, I like this one best because it only has 2 numerical coefficients, and the others, some of the others had 3. Some of them were just terrible, and I don't know why. But they were, and if you'd like to see, there's a macro in here that can optimize these A and B's can be optimized by a macro that uses simulated annealing, or you can just use the Excel solve function. Either one will work. So for people that want to experiment with curve fitting, this is kind of a neat little, Excel is a neat little platform. It'll do a lot of stuff for you, and I do have MATLAB in here. I never have used it yet for anything. It seems to be a little bit impervious to the beginners. I used MathCAD for many years, but the last 2 versions they sold me wouldn't install, and when I tried to call and get help, they tried to sell me more and wouldn't give me any help. My son is an advocate of R, which I have not yet gotten into. He encouraged me to download. I did download and install it. And now there's another program that's popular in amateur radio circles, especially for simulating the antennas and the electromagnetic fields around them, and it's called Octave. I don't know if any of you have tried that. I just learned today that until now I thought that it only runs on a Unix platform, but I found out today you can get it for Windows too.
It's a free version of MATLAB.
Yeah, it's a free version of MATLAB called Octave. So there's lots of tools out there, and people should do more curve fitting to try to find faster. I mean, these little algorithms. Remember that back in the dark ages of computing, if you wanted to do sine or cosine or log or something like that in your old punch card Fortran programs, these commands didn't exist on a computer. You were actually getting one of those Hastings approximations. So anyway, any other questions? Yes.
The normal deviates are also used in all these genetic algorithms and evolutionary optimization algorithms. So it's not only simulated annealing. You have been.
Yeah.
It's a very useful thing.
Yeah, it's a very useful thing. Yeah, normal deviates should be built into the machine. Hello, Hewlett Packard, you listening? All right.
Richard has spoken.